Now we try to obtain the RMS value of output noise voltage of a network. So we consider this is a linear network with noiseless elements. So this particular network has no sources of noise, or we are letting this has noiseless elements, and we are exciting this network by a noise voltage. So this noise voltage can be written as Vni of t. So this subscript n indicates the noise voltage, and I is the input voltage. So we are exciting this particular network by a input noise voltage Vni of t. And definitely the output across the output terminals can be considered as Vn naught of t. So here it is the noise free system or noiseless. This particular system has noiseless elements. When you excite the network by a noise voltage, the output will also be a noise voltage. So here we are letting this h of omega is the transfer function of the system, the transfer function that relates Vn0 of t and Vni of t. And also assume this S here, this subscript I indicates the input. So we are letting Si of omega is the power spectral density of the input noise voltage, and let So of omega is the power spectral density of the output noise voltage. Then we can write this So of omega is equivalent to mod h of omega whole square into Si of omega. So this is the relationship between output power spectral density, input power spectral density, and the transfer function, or the magnitude squared function. H of omega, mod h of omega whole square is the magnitude squared function. So now we try to find mean square value of the output noise voltage. See, what is this? This is the random noise, a random process. This can be considered as the random signal. So therefore, the expectation of that, or expectation of Vn0 square of t, is the mean square value. So this is equivalent to R of 0, is it? The mean square value can be obtained by substituting tau equivalent to 0 in the autocorrelation function. So this is equivalent to, see, what is the power spectral density of the output noise voltage? That is S naught of omega. The mean square value, which is equivalent to R of 0, is related to the power spectral density of the noise voltage as 1 by 2 pi integral minus infinity to plus infinity S naught of omega du. That is the area under power spectral density divided by 2 pi gives the mean square value of the process. So here the output noise voltage is the random signal. So therefore, the mean square value can be obtained by simply substituting the tau equivalent to 0 in the autocorrelation function. That is nothing but, we know the power spectral density of the output noise voltage, then find the area under the power spectral density and divide with 2 pi. Okay, we will get the mean square value. So this can be equated to, so 1 by 2 pi, so integral minus infinity to plus infinity. What is S naught of omega? Is the mod h of omega whole square into Si of omega is the d1. So what this indicates, if you know the power spectral density of the input noise voltage and the transfer function of the system, we can find the mean square value of the output noise voltage. But we already know that the power spectral density is the even function of omega. Therefore, we can write this as 1 by pi integral 0 to infinity, so mod h of omega whole square into Si of omega du. From the properties of the power spectral density, we know that the power spectral density is always an even function of frequency. So therefore, instead of integrating from minus infinity to plus infinity, we can integrate from 0 to infinity and multiply with 2. So this 2 and 2 get cancelled, we will get 1 by pi. 0 to infinity, this. So this is the mean square value, is it? If you know mean square value, can we find a root mean square value? Simply take the square root of the mean square value. Square root of the mean square value is the root mean square value. So therefore, the RMS value of the output noise voltage is equivalent to 1 upon pi 0 to infinity. This is mod h of omega whole square, so Si of omega d1. Is it right? So therefore, this quantity is the root mean square value of output noise voltage.